Mic check, mic check. We're just gonna test how our audio is. Mic check, mic check. Alright, we are good and we are live. Hello everyone, we're back at it again, conquering physics.
Mic check, mic
practicing
check.
for the physics GRE.
We are good and we are.
And here we are with our third stream. So today we're tackling the third problem. And so what we got right here in this diagram is two blocks. And so we have a block on floor, friction mu1, and another block on the side. And there's friction of these two blocks of mu2. And the thing is we're pushing this block right here. So we're pushing this block and the acceleration from this is going to put a normal force here. And if there's enough friction here, this should hold it up. One thing you could think about is uh, if you have, say, like a ball in your hand and you're just kind of spinning in it, you're not maybe your hand's not big enough to palm it, the friction is holding it up, right? And so that's what's going on here. There's a force right here. If the force is strong enough on this, um, if there's an extra acceleration on this block, then this friction will hold it up and it won't fall down, right? And so we have five answers here, and so obviously we're going to work it all the way out. But since this is training for the physics GRE, you might not have time. You don't have time to solve all the problems. So one quick thing we can do here is basically test out how we can work this out in terms of limiting factors, right? Say that there's um, okay, so we're going to evaluate each of these answers and then we'll work it out. So say that there's no friction here. So this mu coefficient is like close to zero, right? What does it do here? So this thing would mean that we have to have a lot of force acceleration. Let me read out the problem first. So two blocks of mass m and m are oriented as shown in the diagram. The block capital M moves on a surface with coefficient of kinetic friction mu1, and the coefficient of the static friction between the two blocks is mu2. What is the minimum force F which must be applied to M such that little m remains stationary relative to M? And so we have all these answers right here. And the reason why I bring up the limiting factors is because that would just be able to allow us to eliminate some of these answers to see which is right. So if we were to imagine this setup, right, and we have our mu, we have very little friction here. This block might almost always fall down no matter how fast we try to move, right? It's like super slippery. And so that means we're going to need a lot of acceleration to attempt to hold this up. And so as mu kind of approaches zero, this gets really, really large. So this one somewhat makes sense. It doesn't mean that it's right, but we can't throw it out right away. Same thing for this one for part B. And for part C, as mu2 goes to 0, this is going to be a constant. And that doesn't make sense because if literally mu2 is actually 0, it's saying that you'll be able to hold it up. And that's impossible. This thing will fall down with whatever velocity or acceleration you have, even if it's near infinite. So this one doesn't make sense. So C, right away, we can kind of disregard it. And so with D, this still holds true in the sense that if mu2 is really, really small, then uh, we'll have this part will blow up, so that's fine, as these will blow up. And for E, we have the same thing too, where this two will blow up. Okay, so that's enough with that part. So now let's say if it's really, really large, then here's another aspect. If mu2 is very large, then we might actually not need too much force. So the force could be a lot smaller. And we kind of see that in this one. If mu2 is very large, then the force required to push it uh, isn't much needed. Same thing with B. With this one though, thing is, again, we have the problem where if mu2 is very large, this drops off to zero, and we're left with a constant force. And that doesn't necessarily make sense because this thing should almost be able to held up on its own, even with just a little bit acceleration, if we had take mu2 to be infinity. And so this one we could probably write off. And probably the same thing goes for this one as well. So we know our solution will end up being one of these two, right? We could probably make more arguments just for the sake of attempting to try to solve this quickly. Um, and obviously, if you practice enough, you'll be able to figure this out on your own. But we're here to train. We're trying to become mathletic. We're trying to build up our math skills and our physics intuition, right? And so another thing we could do is just look at, okay, well, what happens if we make the mass of each of these different, right? If we make the mass of this big M much, much larger, then in order to put an acceleration on this one, we're going to require a lot more force. And as we can see on this one, it's not dependent on big M. That kind of doesn't make sense. Let's say that if this M is just so massive, it's so hard to push this to even be able to hold this up, then um, we should have to put a lot more force. This isn't proportional to M in this case. That kind of doesn't make sense. And when we look at B, um, when M is very, very large, what we notice is that this might almost, uh, the limit of this will cancel out with this. So the limit actually does end up approaching this, which is the acceleration needed to hold that up. This is making a little more sense. And we could kind of go in the other direction that if this M is very, very large, we still might need a lot of force because we're just pushing the whole thing. And so if this part's very large, we could then again see that in the limit of this, then it's dependent on some other factors. So we're not entirely sure. Personally, I would end up choosing B as the answer, but let's actually work it out to see if it's true. And so we do this by doing a force body diagram. And so we'll look at the forces on this little m. And so what we know is that the sum of the forces in the x direction and the sum of the forces in the y direction. Okay, so we know that there is a normal force in this direction because it's getting pushed by this block, right? And so we'll say this is the x direction and the y direction. And so this is going to be MAX. And so this is going to be equal to just the normal force, right? And when we look in the y direction, what are the two forces acting? In this case, we have so we have gravity, which is going to pull it down. So we have minus mg, and the force that's going to be hopefully holding it up. It's going to be a frictional force, right? And so this frictional force, uh, as we know from our studies, this equation ends up being mu times the normal force. So the coefficient of friction times the normal force. And in this case, which mu will we use? Mu1 or mu2? Of course, mu2. And because it's the friction between these two, right? And so in this case, though, this what the problem specified. So let's go back to the problem itself. What it asks is, what's the acceleration needed to prevent the block from falling down? Yes, is what is the minimum force that must be applied such that it remains stationary? And so if it's remaining stationary with respect to m, then what's needed is to know that the acceleration is 0 because it's not moving, right? And so now that we have this, we can set these two things equal to each other, and we have mu 2n is equal to mg. And we know that this acceleration xa is equal to this n. So we could then use mu2 going up here, and we'll have max. We just leave this for now, because now we're going to want to look at the force body diagram of this block being pushed, a big M. Okay, and so in this case, we have the force that we're applying, right? And we do the same thing, where we're going to apply Newton's equations in the same fashion. And so we have a normal force from the ground pushing it up, and we have gravity pulling it down. And so we make the distinction of using the big M. And in this case, since we have this little block actually pushing back, which is going to be the normal force that we're talking about in this case, okay? And so when we do the sum of the forces here again, we separate the x and we separate the y components. So in the x direction, we have the same acceleration, so it's actually going to be the same ax. And so because we're assuming that they're attached, so this ax is actually going to be the same as this ax. Okay, and so this is Newton's law. The sum of the forces is equal to the acceleration on the system. And in the x direction, we have our force applied in the positive direction. And then we have minus the normal force from the little box, which is the same n here. Okay, and so for this y direction, what we recognize is this box isn't going into the floor, right? It's being held up. So we can say that the sum of the forces is equal to 0. And when we look, we have the negative for gravity pulling it down, and then we have the floor, the frictional, holding this thing up. Well, not frictional. We have the normal force of the ground. So one thing I just realized is we have another force acting on this box that I almost forgot about. We have frictional force pulling this thing backwards. And so this is going to be negative F friction. And in this case, the way we write that is going to be related to a normal force as well, but it's going to be the normal force to the ground. And this one's going to be mu1 ng. And so this is related like this. And so what's ng? Well, we could solve it from this part. So we get ng is equal to big M g. So this is g for gravity, and this is just the subscript. It was supposed to denote for the ground. We could then plug this part into here to then solve for this. So we have big M ax is equal to the force we're applying and we want to solve for the minimum, right? This minus mu1 ng, which we're plugging in, big M times the gravitational constant. And now that we actually have this this ax, we can solve for it and we can divide everything out by m. So ax is equal to f over m minus n minus mu1 g. And so when we plug this thing into here, what we end up getting is mu 2 m, and then we get this whole mess right here, f minus n. Hold up, this n we had already solved for. So let's plug that stuff in. Let's clean up our equations before we go any further, right? Let's try to make this neater. So this ax is equal to f minus this is equal to, what do we say? This is equal to m ax. Oh, so in that case we shouldn't move it over yet. We're just finding some stuff on the fly. So we're actually still going to want to work with this equation right here. So the reason why is because there's going to be an a that we're going to want to factor out. We have ax is equal to f minus little m ax, and these ax's are the same. Mu1 mg. And so here we're actually going to want to factor it to the other side. And then we can factor out the a here. We'll get m plus m ax is equal to f minus mu 1 mg. So ax is equal to this mess. G over m plus m ax. Nope, the m ax remains. We just divided by this side. Okay, so even though we would think, oh, we have to plug this into the other one, we could actually just go the other way and actually plug this mess into here. It might make it a little easier. So I'm just going to rewrite this part over here. So this is mu 2 m a x is equal to mg. So let's actually solve for ax and then just plug it here. I think that might make our life a little easier. So one thing we see right away is that these m's cancel out. We get mu 2 ax is equal to g, and so we can say ax is equal to g over mu 2. We could plug this in on this side, and then we get g over mu 2 is equal to f minus this. So let me just double check something real quick. Okay. Make sure we're not missing anything over here. Okay. And then what we want to end up doing is solving for f, right? And so let's maybe look to see if we have anything related to our answers. So we do have an m plus m. Let's see if we can get this part out. And so when you end up trying to solve for this, we're going to want to multiply this out. And we'll get g over mu 2 times this is equal to f minus mu 1 mg. And then we can subtract this part out over here. Or add it, my apologies. Okay. One thing that's interesting is there any factors that we can pull out from here? So this is the f we get, but it looks nothing like anything we have so far. But let's keep working it out. It's actually looking like it would be one of these other ones. Let's double check our work, all right? Because here we're not going to hide our mistakes. Okay, so let's start from the beginning and double check. So we go here. When we did the sum of the forces, let's make sure we're not forgetting. We have the normal force here times the direction. Okay, this is solid. We're looking at these two directions. We have mg and the frictional force. That's what we got. We said it's equal to 0. And so we had mg is equal to the normal force times that. The normal force is equal to m in the acceleration, which makes sense because we're pushing the block in this direction. We had gotten it from this. Okay, and so we had rewritten this here, basically saying that AX is equal to um, this part. That makes sense. So this is just basically what we solved in the beginning. So if we were to have an error, it might end up being here. So when we look at the big block, there's 3 forces applied on the x direction. We have the force that we're pushing into, the normal force of the little block that's attached to it, and then the frictional force that's pulling back. So we have F minus N, which is a little box. And then we have mu1 ng, which is this. And we solved for ng here when we looked at the sum of the forces in the y direction, which is ng minus big mg, and that told us that ng is equal to big mg. We can plug this into here, and so we have this equation to get to here, and then from here we end up going here to show that we substituted this n for max. And so this looks correct so far for this equation. We factored out the ax here, and then we divided. And we actually probably should have just plugged it in here. It would have been easier. So let's just do that. Plug it in there, so we could avoid some potential algebra errors along the way. So we would have plugged in g over mu2 here is equal to f minus mu1 mg. Okay, and that tells us that f is equal to mu1 mg plus big M plus little m g divided by mu2. Okay, and so if we were to kind of distribute this thing out and then factor out even more, let's see what we end up getting. We end up getting, we could take out a g from the whole thing. Let's just factor out first. We don't want to skip too many steps. G, okay, mu1 mg plus big M over mu2 g, so we're distributing right here, plus little m g over mu2, and let's see what we have for potential answers. So now what I'm looking is some of these other ones might actually be potential solutions, so we have to really take them into consideration. What's interesting is we might have made a wrong assumption somewhere along the lines, but this looks pretty interesting right here too. D. Let's see, is there any way we could factor this stuff into any of those? So at least this part right here, we can get the mu1 plus 1 over mu2 times big mg, and here we have mg over mu2. So I think this might actually be one of the answers. Not quite. So here, if we actually had another, let's see. If we had another mu1 term for the little m, we would be good. So let's try to find that to see if that's what we're missing. So in trying to find this out, we can go back and check our work. Okay, so what would be the term that we're missing, if this is in fact the answer? We're missing the mu1 and little m. Okay. So here we say there's 3 forces. Is it possible if there's more forces in the x direction? So let's think. There's a normal force pushing on this block, up and down. Boom. I think we're fine here. It's this one I could be a little worried about. Oh, I see. Okay, so this is another flaw, and so this is why it's good we go over this stuff. So the little box itself is also applying a frictional force. So the little box is being held up, right, with frictional force, which means it's holding this thing down with the frictional force. Which means in the y direction we actually need to include a minus F this. And this frictional force is going to be the minus that we're looking for. It's going to be minus mu2 n. Because right here it's plus, so this is going to be the opposite. And so when we solve for ng, this should actually end up being ng is equal to that plus mu2n. Okay, so it's gonna change what we have, and so right here we had actually only plugged that in. So we'll actually take this equation and move it, plug this into this part because this is where we plugged it in. Um, or we'll just look back at this equation and plug this into here. That's what we'll do. Sorry, it's a little messy, but we learn, we live and we learn. Okay, we have F minus N minus mu1 ng, and then we had solved that ng is equal to this, and we know that n is equal to um, a max, right? So we have F minus max minus mu1 ng is equal to mg plus mu2 n, which we know is max. And so let's just simplify all the terms first before we start moving things around. Minus ax. So we distribute this. Mu1 mg minus here mu1 mu2 max here, and then we can move all these terms over and leave the f on one side. Oh wait, before we do that, we might want to plug in what ax is. So we had solved previously that ax was g mu2, and so let's just plug everything in right now. G mu2. I know the mu's look like m's. Bear with me. Oh, and there's an a right here, which this a becomes g over mu2, which will cancel out these mu2's. And guess what we have? So we'll move this f to the, we'll add everything else to the other side, so they're all positive terms now. And we'll just start with this one. Big M G mu 2 little m G mu 2 big M G mu 1 up top, and this is going to be positive because we moved it over. This is going to be positive little m G mu 1. Boom! And this is what we wanted to find. So when you factor out this, you get this. You factor out this, you end up getting this. And then from here, you can then factor out the m, big M plus little m out. And you get mu 1 G plus 1 or plus G over mu 2G. And this is what our force is. So F is equal to this. What's neat is this actually ends up being D. So my intuition initially failed me. And these did seem a little off when I was kind of looking, at least in the initial estimation. That was my first guess. So that's why intuition could be good sometimes, but it could also lead you to your downfall. This is a prime example of of why you might not want to trust that. or you just gotta get sharper and solve these faster. So this one that I had ruled out actually was the answer. So this one in this case was D. Um, but I hope this one just kind of worked as a testament to all the different things you have to take into consideration. Um, and so they're a little more complex than you'd first imagine. This little box was simple, but here we have to remember that there's forces, there's an equal and opposite force that acts. So the frictional force that was holding this up is pulling this one down. Um, and yeah, this is a pretty neat problem. Took a lot longer than we would have anticipated. We'll get better at them and be able to cut down our time, and hopefully we can have better presentations. I hope this was a fun little learning experience, and yeah, enjoy. Have a good night.